Welcome dear students to this program. Today we are going to discuss from class 9 mathematics book from chapter 10, that is on circle part 2. In earlier class we have studied or discussed about the different terms of circles. The terms we discussed are radius, center of the circle, diameter, chord, arc, minor arc, major arc, then segment, that is minor segment and major segment, and also about sector and minor sector, major sector, and semicircle, semicircular region. Today we are going to discuss some more terms like angle subtended by a chord at the center and angle subtended by a chord at any point on the circle. So let's try to understand what do we mean by angle subtended by a line. So let's look at this figure. Here AB is a line and line segment, and a point C is not on the line containing AB. Then if we join AC and BC, then we can get an angle that is ACB. So angle ACB is called angle subtended by the line segment AB at point C. Now let's come to chord. Here the figure shows that AB is a chord of the circle with center O. Now in this figure you see, apart from AB we have two more points C and D. So AB subtend angle both at C and D. C is a point on the circle, so angle ACB is called the angle subtended by the chord AB at the major arc AB, because that point is on the major arc. Similarly, if we consider the point D on the circle, angle ADB is also the angle subtended by the chord AB, but in this case it is at the minor arc AB. Now AB is, in this case, again AB is a chord and the center of the circle is O. Then here you can see that AB also subtend angle at O. So we can say that angle AOB is the angle subtended by the chord AB at the center of the circle. Now consider two chords here, CD and AB. As you see, these chords are unequal. CD chord is greater than AB. The angle subtended by CD is COD, that is at the center. Similarly, the chord AB subtend the angle AOB at the center. Which is greater? The angle COD is greater. So we can say if chord AB is less than chord CD, AOB is the angle subtended by the chord AB at the center of the circle, and COD is the angle subtended by the chord CD at the center of the circle. Then angle AOB is less than angle COD. That means the greater is the chord, the greater is the angle subtended at the center. Now you see, if the two of the chords are equal, what can we say about it? Whether the angles subtended at the center be the same or not. And this shows by the statement of this theorem. This theorem states that equal chords of a circle subtend equal angles at the center. Again, we read it. Equal chords of a circle subtend equal angles at the center. So in this statement, what is given? In this figure, we have given two equal chords, that is AB and CD, and the center of the circle is O. AOB is the angle subtended by the chord AB, and angle COD is the angle subtended by the chord CD. Now, what to prove? We have to prove that the angle AOB is equal to angle COD. Now, as you see here, we have two triangles. We can prove the congruency of these two triangles. So, let's prove. Here, in triangle AOB and triangle COD, what are equal? As you see, AO is equal to CO, BO is equal to DO, and all these four are same as the radius of this circle. And again, what else is given? We have AB is equal to CD, as they are two equal chords. So here the two triangles are congruent by side congruency. As the two triangles are congruent, so their corresponding parts are also equal. So according to that, we have angle AOB is equal to angle COD by CPCT, means corresponding part of congruent triangles. Now let's see, if two chords of a circle subtend equal angles at the center of the circle, are they equal? So this is just a question that verifies the converse of the last theorem. Now, so the converse of last theorem states like this: if the angles subtended by the chords of a circle at the center are equal, then the chords are also equal. Now, what is given in the figure? You see, here we have two chords AB and CD, and they subtend angle AOB and COD at the center. So in given part, we can say that AB and CD are two chords of circle with center O. Angle AOB and angle COD are the angles subtended by the chords AB and CD at the center respectively, and angle AOB is equal to angle COD. Now, what to prove? We have to prove that AB is equal to CD. That means the chords are equal. Now again here we will take the same two triangles for congruency. In triangle AOB and triangle COD, as in previous case, AO is equal to CO, BO is equal to DO, and all these four are same as the radius of the circle. And the third condition is AOB angle is equal to COD angle. So what next? Triangle AOB and triangle COD are congruent, and here the congruency is by side angle side congruency. As two triangles are congruent, so their corresponding parts AB is equal to CD. So we proved these two theorems. Now let's have some application of these theorems. An isosceles triangle ABC is inscribed in a circle with center at O. If AB is equal to CD and all the sides are on the same side of the center, show that OA bisects the angle subtended by BC at O. So let's draw a circle, and the angle is, the triangle is inscribed in it such that AB and AC are equal, and BC is the third side. O is, the center is here. So AB, AC and BC are on the same side of the center. So we have to show that the angle subtended by BC at O is given by joining BO and CO, means angle BOC. So what is given in this case? In triangle ABC, AB is equal to AC. Triangle ABC is inscribed in circle with center C, with center O, and angle BOC is angle subtended by side BC at O. What to prove? We have to prove that AO bisects BOC angle. So we have to draw this AO. Now you see proof. See, AB is a chord and AC is another chord. So the chords in the circle, the chords AB is equal to AC. Why? They given. This is given. This implies the angle subtended by AB and AC at O are angle subtended by AB and AC at the center O are equal. This implies angle AOB is equal to angle AOC. Now see, angle AOB is equal to angle AOC. But these two are angle AOB and angle AOC are adjacent angles. That means these two constitute another angle, that is BOC. This implies AO bisects angle BOC. You see, by using the information or data that two equal chords subtend equal angles at the center, we can easily prove it without using the congruency theorem. Now let's see another example. Two circles are said to be congruent if they have the same radii. Here we discuss this because our next questions is related to this. Prove that equal chords of congruent circles subtend equal angles at their centers. So you see, as we know, two circles are said to be congruent if they have the same radii. So we can draw two congruent circles, that is two circles having same radii. Say first circle is S and the second circle is S dash with the centers P and Q, and they have equal chords. So say here AB, and in the next one say CD. So what is given here? It is given that S and S dash are congruent circles with centers P and Q respectively. AB and CD are chords of circles S and S dash respectively, and also AB is equal to CD. Now angle subtended at center by AB is angle APB. Similarly, angle subtended by chord CD at Q is angle CQD. So we have to prove angle APB is equal to angle CQD, as these two are angles subtended by AB and CD respectively. Now we have to prove, as in previous theorem we discussed. Let's start with the proof. Here we have two triangles. Let me write this P here and Q here. So in triangle APB and triangle CQD, we have AP is equal to BP, which is again equal to CQ is equal to QD. Here BP and CQ are radii of congruent circles, and APBP are radii of same circle. Similarly, CQ and QD are radii of the same circle. So we can say radius of congruent circles. Now, and the third condition is AB is equal to CD, and AB is equal to CD. This implies triangle PAB is congruent to triangle QCD. This shows that as two triangles are congruent, so their corresponding parts are also equal. So here this congruency is by side congruency. And this implies angle APB is equal to angle CQD by corresponding parts of the congruent triangles. So here again we proved the same thing, but if the circles are congruent, then that theorem also holds good, that if two chords of congruent triangles are equal, then they subtend equal angles at their respective centers. Now let's have another question. The question is, prove that if chords of congruent circles subtend equal angles at their centers, then the chords are equal. So let's see, we have two congruent triangles here. One is say S1 and let the second one is S2. If P is the center of the first circle and Q is the center of the second circle, and we have two chords A, B and C, D respectively in S1 and S2, they subtend equal angles at their center, respective centers. Means APB angle is equal to CQD angle. If these two angles are equal, we have to show that the chords are also equal. So what is given? Here P and Q are centers of circles S1 and S2 respectively. S1 and S2 are congruent circles now you see angle subtended by chord AB, so we have to write AB and CD are chords of circles S1 and S2 respectively, such that angle APB is equal to angle CQD. AB subtended angle at P, APB angle, and angle subtended by CD at the center Q is CQD angle. These two are equal. So what to prove? We have to prove that AB chord is equal to CD chord. Now let's see, here also we have two triangles, so we can prove the congruency of these two triangles. So how to prove congruency? In triangle PAB and triangle QCD, what are equal? PA is equal to QC, radii of congruent circles. Similarly, PB is equal to QD, the reason is the same, radii of congruent circles, and the angle APB is equal to angles CQD. It is given. So this implies triangle PAB is congruent to triangle QCD. Why? By side angle side congruency. two sides and their included angle is given. So this shows that AB is equal to CD because these two are corresponding parts of congruent triangles. So thus we proved that if chords of congruent circles subtend equal angles at their centers, then the chords are equal. Dear students, today we discussed about the angle subtended by a chord at the center, and also we could understand the angle subtended by a chord at the circle, at different points of the circle. And using this, we proved some theorems on equal chords and their subtended angles at the center. I hope you understand it better. Thank you.